Okay, welcome. We are now going to take on Chapter 2, which is the chemical level of organization. So this is where we're going to start off with basically that hierarchy of organization going from atoms and then into molecules. So let's get started. What is matter? Matter is anything that takes up space and has mass. When we say mass, what is that? Weight? No. It's only the quantity of matter in the object. Weight is a tricky thing to keep in mind. You can have mass without weight. That's what astronauts deal with in outer space because there's no gravitational pull. Weight is dependent on the gravitational attraction of the mass. You can have a 200-pound person and they would be approximately somewhere in the range of about 35 pounds on the moon. That's because the moon has 1/6 the gravity of Earth. They still have the same mass, okay? The quantity of matter, but the weight would be much different. Now, all matter is composed of atoms. We know that, and we'll go into that. There are three basic types of matter: solid, liquid, and gas. Now, when you talk about atoms, what are atoms? Basically, you have a nucleus, and then you have this electron orbital here. A lot of times when you see these things, you're going to see them like moving around like a planet and a star system. That's been totally tossed out as a model. Unfortunately, it's still used even on the nightly news. Why? Because everybody is kind of remembers it. Let's go over this though. In the nucleus, you're going to have one or two types of particles. You're always going to find protons because they're positively charged. Neutrons have no charge. They have about the same amount of mass. Now that's about 99.9 or 0.8% of the mass of the atom. The rest of it are these very small but equally opposite charged particles called electrons. In other words, if a proton is here and it's +1, the electron out here is -1. So what we do is, instead of these circling orbits, etc., we refer to this now as electron clouds, because at any moment, statistically, the probability of the electron will be somewhere in this range, but not always predictably. In other words, you can't always observe it. Instead, sometimes they'll also call it the electron shell representation. It's either electron cloud or electron shell. Now, isotopes, what about those? Well, think about it this way. Isotopes have the same number of protons, but a different number of neutrons. It doesn't change their chemical properties. It may change the mass of the atom, but if you look here, you have three different isotopes of hydrogen. Hydrogen 1, all it's got is a proton. Remember I said sometimes you only just get one with a proton? Here it is. So, and the charge is balanced out and basically canceled out by the negatively charged electron out here. Okay, so this is one atom of hydrogen. Here's another atom of hydrogen, but it's an isotope. It contains actually one proton and one neutron. So if you notice the mass number here, it's 2. But neutrons have no charge, so you don't need anything out here, the electron shell, to cancel out a charge. So it's still one proton, one electron. You have the third isotope, which is really tritium. Now, tritium, hydrogen 3, it's going to have 2 neutrons, 1 proton, 1 electron. They'll all act the same chemically, okay? The only difference is that tritium, and we're going to get into this in a little bit, is somewhat unstable, and so it's radioactive. We'll get more into that in a few minutes. So how do we get these incredible numbers when we look at a periodic table and you see 1.00135, etc.? How can you have a 0.0035 of an atom? Well, what happens is that in any sample of any element, you're going to have a mixture of different isotopes. One will be the predominant one will be lesser, and there actually may be many. As a matter of fact, sodium has 10 isotopes. You have different ratios of isotopes which affect the atomic weight of the element. As you can see here we have a sample, the atomic weight of hydrogen, 1.0079. Wait a minute, you can't have a 0.0079 atom. But what they do is they take the ratio here, because out of, let's say, 5, that's 9, that's 12, and that's 14. Okay, so you take out so many of these out of your sample, and you're going to have once in a while a little bit of deuterium and a little bit of tritium. So that's going to kind of shift this upwards from 1. Okay, now moving on. Elements of the body. Recently, they have upped the number to include bromine. Okay, but basically there are 28 elements that make up your body. They used to have a somewhat of a humorous research paper that was published where this researcher basically took the total cost of each element that made up a human body. And interestingly enough, he came up and said, yep, based on the chemical sales, the sale of each sample of chlorine, magnesium, sulfur, oxygen, nitrogen, carbon, et cetera, et cetera, et cetera, you would be the $6 million man or woman. Okay, depends on which program you like. And that also included all the trace elements here. Bromine's been added because they found that bromine plays a role in 1 or 2 unique enzymes. Yep, there's vanadium down there. That plays a role in the function of a couple of enzymes, which we'll talk about later on. It's a cofactor, as magnesium is a cofactor. But here's an interesting one. If you look down in here, you will see some really strange ones. Cadmium. I thought cadmium is a poison. Yes, in larger quantities it is. And you have sodium and potassium, and you have iron and iodine, and you continue to go through all these. Now look, first off, I'm not expecting you to memorize all the chemical symbols, but it helps you to be familiarized with some of these. You are going to have them revisited throughout both AP1 and AP2, okay? Particularly things like Ca for calcium, P for phosphorus, N for nitrogen, hydrogen, carbon, oxygen, sodium, and potassium. Potassium is K. Why is it K? Well, when they were doling out the symbol letters, phosphorus got P, because phosphorus was actually the 12th element kind of discovered. When you get previous to that, the elements are considered prehistoric, meaning before recorded time, that they have been known to exist. Also, some of the original names for the elements were based on their compounds, which were in Latin. Potassium, for example, was calcium. Sodium was natrium. And so when they first started setting up these designations, they used that symbology also. Iron was ferrum. Okay? So it will help you to get familiarized with some of these, not only the element, but the element symbol, and what is some of the significance of them. Now, radioisotopes. These are isotopes that are unstable. Now, if you go back to tritium, by the way, I've worked a little bit with tritium. Tritium is a hydrogen isotope that is unstable, which means that roughly every 12.5 years, your sample of tritium will break down. What do I mean by that? The nucleus breaks down, and this is called radioactive decay. It may give off energy or matter. It may give off a neutron or a proton. It may kick out an electron. It may kick out a photon. But under these conditions, half of the elements, or half of the atoms in any sample will break down, and they will undergo radioactive decay. And this is what we mean by half-life. This is the time required for 50% of the sample to undergo radioactive decay. So if I had, let's say, 1 liter of tritium, in 12.5 years, I only have half a liter. Now, in another 12.5 years, I have only 1/4 of a liter, because I have 50% of the remaining undergoing radioactive decay. And this continues. I used to work as a nuclear chemist at one point in my fancy career, but this is something that you have to keep in mind because we're going to talk about use of radioisotopes as therapeutics. And sometimes the short-lived isotopes, those that have very, very short half-lives, are very beneficial, not only because they're going to be very specific with their radioactivity, but because very quickly afterwards they're going to be basically broken down and will not be lingering in the body of the patient. Now, we have to understand a couple of other properties here. Electrons will occupy various energy levels. In the first electron level, you can only put the maximum of 2 electrons here. So hydrogen has 1, and if there's a second one here, such as with helium, you have 2 protons, 2 electrons. This means that you can't add any electrons, nor will they be able to pull them away. Therefore, helium becomes what is known as a Nobel gas. It is non-reactive. They use helium in some cases because it will not have chemical reactions such as burn or corrode or anything else. Now, with the next element up, we get into the next energy level. This energy level can have a maximum occupancy of 8 electrons. Now, with lithium, it only has 1, 2, 3 protons, so you're going to have 1, 2, and third one will be in the next energy level. You can create compounds by adding or taking away or sharing electrons, and as a result, you can form compounds with lithium, lithium chloride, lithium oxide, etc. But when eventually you get to a full energy level here, this is where you get into the next Nobel gas, neon. Neon has 10 protons and has 10 electrons. The first 2 are in the first energy level. The other 8 are in the outer next level, and this is what we call valence electrons. We also refer to this as the octet rule, this property whereby this outermost energy level can be maximally occupied by 8 electrons, and that plays a role of whether or not you're going to be able to be chemically reactive or not chemically reactive. Okay? In this case, neon gas is not chemically reactive. And as I mentioned before, we were talking about valence electrons, and you can see here's the valence electrons. The octet rule is very important in understanding chemical bonding. Now, chemical bonding, we're going to talk about several different types. When you have atoms either lose electrons or have more electrons than compared to the protons, that is when you go from being an atom to an ion. Let's take a look at this example. Here's a sodium atom, okay? Its outermost valence electron shell has only 1 electron, but this has 11 protons. Well, it's a nice stable atom. Should it lose an electron, that means it has more positive charges here than negative charges out here, and as a result, it has more positives than negative, and therefore it becomes an ion, a charged atom. In this case, it's positively charged because it has more positive charges in the form of protons than it does of negative charges of the electrons. Now, everybody ready? We're going to move with chloride or chlorine. Now, in chlorine, its outermost valence shell, that's where the valence electrons are, has 7. Remember, we need 8, the octet rule. Okay, oct meaning 8. Now, what we're going to do here is we have, 7, we have 8 here, and we have 2 there, so we have basically a total of 17 electrons, which means you have 17 protons. Everything is nice and stable. The positive charges are canceled out by the negative charges, so it is a nice neutral atom. But if I add an electron to this, now I have more negative charges than positive charges, and I have a chloride ion instead. I went from a chlorine atom to a chloride ion. Now they're stable. What they mean by that is that now these have achieved a level of stability, but you've got positive attracted to negative. Keep this in the back of your mind. Opposites attract. Yeah, I know. Not necessarily in dating, but in chemistry, that is a key point, especially when we start having oppositely charged ions. Okay? Now, how do we form chemical bonds? The first type of chemical bond we're going to deal with is ionic bonds. This is based on a chemical bond where you have bonding attraction of oppositely charged ions. Okay? You can't have positive and positive. They're not going to be attracted. They're going to actually repel. It's just like poles of a bar magnet. You know, you can't have the south attracted to the south. It will be attracted to the north part of the bar magnet. Okay? So the sodium atom reacts with the chloride atom. There is the sodium ion formed where it loses an electron. The chloride atom, the chlorine atom picks up that extra electron, becomes a chloride ion. You now have a positively charged ion, the sodium ion, a negatively charged ion, the chloride ion, and now you have formed literally table salt, sodium chloride. Okay? Now, one other key point here. This is a very strong bond, but it can be dissociated, separated by polar molecules. We'll get more into that in a few minutes. Just hang in there. The other type of chemical bond we call is covalent bonding. Now, ionic bonding, you've grabbed an electron or you've lost an electron, and it's strictly bonding attraction by oppositely charged ions. Covalent bonding is sharing. We're going to be sharing now. Bonding due to the sharing of a pair of electrons between the atoms. Now, I'll get more into this in a second. Let me focus a little bit more on just the ionic bonds, because this is where you get these wonderful crystalline structures, sodium chloride, and a variety of other compounds. If you notice in here, this is just one crystal of sodium chloride. Notice how they're nice, neatly packed, where you've got chloride ions surrounding a sodium ions surrounding a chloride ion, and they're all bunched together. They're all attracted to oppositely charged ions, and this bonding affects the compound structure. In this case, you get this cuboidal or cube-shaped sodium chloride. Now, covalent bonds, sharing. Okay, sharing a pair of electrons. That means that basically you have a pair of electrons that basically orbits between one orbital in this atom, one orbital in that atom. That is a single covalent bond. By the way, we went from hydrogen gas, let's go to oxygen gas. That's what you breathe every day. Oxygen, O2. How is it O2? Because in this case, you share two pairs of electrons between them. Now, here's the way to think about it. Remember that the innermost electron shell, which is the only electron shell for hydrogen, can take a maximum of two. So basically the two get shared between here and here. Once we get into a second electron arrangement, or electron shell, valence shell, you have to have a maximum of 8. So if you look on this orbital for this atom, 1, 2, 3, 4, and then the shared pairs make 5, 6, 7, 8. And so this pair and this pair basically revolve back and forth between one oxygen atom and the other. This is forming what they call a double covalent bond. Each single bond is a pair of electrons. If you have a double covalent bond, you're sharing 2 pairs. If you have a triple covalent bond, you're sharing 3 pairs of electrons between the two atoms. Now, you can take a look at how this works. A lot of covalent, a lot of compounds have covalent bonding. For example, carbon dioxide. Now, if you notice here, here's carbon. Carbon basically has 2 inner orbital electrons. They're not playing a role in anything. But it has 4 on the outside here. So it needs a total of 4 from its neighbors to achieve stability of this outer electron arrangement. Guess where this is coming from? You have one pair here and one pair here. So 2, 4, 6, 8. And the relationship or the bonding between this oxygen atom and this carbon is stable. You have 2, 4, 6, 8. And you notice that there's stability here as these pairs shift between back and forth. Now, by the way, 2, 4, 6, 8, they will also rotate and be shared by this carbon atom, which means that you have basically a carbon atom that has 2 double covalent bonds, one a double covalent bond set up here, one double covalent bond set up here, okay? Chemical bonding is extremely important, but furthermore, is what we call the geometry of atoms and how they set themselves up. Now, this is where we're going to get to actually explain why water is so weird, and yet at the same time, water molecules are essential for life. You're going to have situations where you have unequal sharing of electrons between atoms. This creates an asymmetrical polar molecule, meaning it is warped, it's not symmetrical, okay? In this case, what you have here is that you have a hydrogen atom here, you have the oxygen atom here. You have a hydrogen atom here and an oxygen atom here. You will have one oxygen electron shared with this hydrogen because hydrogen has one electron. Its inner shell will be filled by 2. Same thing with this relationship here. This oxygen will have one electron and the hydrogen will have one electron, and they will occupy this very briefly. But guess what? The more powerful, the larger, the more massive the atoms, the more often they're going to hold on to electrons compared to small atoms like hydrogen. And so what happens is oxygen is the big bully. This is this concept you may have had in chemistry called electronegativity. What basically it's saying is this: I have more protons, I have a larger arrangement for a valence electron shell. So basically this pair of electrons that goes between oxygen and hydrogen is more often going to be over here than over here. Same thing with this relationship with this hydrogen atom and this oxygen atom. So think of it this way. Here's a pair that goes once around here, but then goes once, twice, 3 times around the oxygen atom before it comes back here. As a result of this unequal sharing, you tend to have somewhat of a more positive pole on this side, and that's what the sigma plus is symbolizing. You have more of a negative pole, in other words, a slight unequal sharing of the electrons leads to sort of what they call a dipole. In other words, you're going to get a molecule that is somewhat negative on one side and somewhat positive on the other. And that's what you see with this oxygen atom. The bigger part of the oxygen atom will be negative over here. This side will be positive over here. Now that's water. But guess what? Because of the unequal sharing of the electrons, this is going to create what we call an asymmetrical polar molecule. Now, polar molecules will have a weak bonding between each other. This is where we get into what we call hydrogen bonding. This is extremely important to understand. You need to get this down cold, hard, and fast. Hydrogen bonding exists with water molecules, but it also exists with the different strands of DNA and when RNA folds upon itself. So you need to know this. This is what we call intermolecular, between molecules. Hydrogen bonding is still comparatively weak when you compare it to something like an ionic bond or a covalent bond. But here's the thing. Because this is unequal and it's somewhat positive more on this side and negative more on this side, that means it can have an interaction with its neighboring similar molecules. So the positive on this side gets attracted slightly to the negative on this side. This creates unique properties that you see with water. Okay? Now, when you spread this out, you have really three different types of bonding. Ionic bonding, it's complete transfer of electrons. You end up forming positive ion and a negative ion. That's the attraction of separate, oppositely charged ions. Nonpolar covalent bonding, I'm going to the far end here, is equal sharing of the electrons. So basically the electrons are passed between the carbon and the oxygen and the carbon and the oxygen very equally. So the charge is balanced out among the atoms. Okay? So you'll have electrons go from this oxygen to that carbon and back and forth. Now polar covalent bond is sort of like this in-between. And it's not as much in-between from the ionic bond, but this is what you're going to have, an equal sharing of electrons. So the electrons are shared between this oxygen and this hydrogen, but more often the electrons are going to be over here, creating this somewhat negative dipole, slight negative charge here. Because the electrons are transferring from hydrogen to oxygen, you're going to have the hydrogen side be slightly positive. This is the dipole of positive. So you're going to have an unequal distribution, a dipole, or a slight positive charge on one side of the molecule and a slight negative charge on the other side of the molecule. Sorry about that. Here we go. Now, as I said, polar molecules have a weak bonding between them. So this is called hydrogen bonding. And the interesting thing with water is that this accounts for a lot of different unique properties. Water is the universal solvent, everything that can dissolve in it. And if you understand, like I mentioned before, water is one of the things that everybody is looking at different planets and moons and everything else for. Not because, hey, we can go up there and get a drink of water if we're astronauts up there. No, it's because water may offer the potential now, for life existing. Now, with DNA, the molecules or the strands of DNA are kind of held together by hydrogen bonding. Again, very weak, but each strand has an attraction to the other strand. We'll get more into that later. The intermolecular bonds between molecules now affects the physical properties of compounds, and this includes the physical properties of surface tension, melting and boiling point, solubility of ionic compounds. Because water is a compound that is a polar molecule, it can get between the molecule, the charges on the molecules can get in between the different ions and disrupt the bonding of ionic compounds. Melting and boiling point, real simple. If I was to take, instead of dihydrogen oxide, otherwise known as water, H2O, and instead went down the periodic table where I don't have hydrogen bonding, such as dihydrogen sulfide or H2S, or going down to H2SE, or going down to H2TE, you get them as gas because they don't have a lot of intermolecular bonding at room temperature. Water, if you rule out, or you're some way able to rule out completely hydrogen bonding, water would also be at room temperature a gas, but it's not. It's a liquid. As a matter of fact, if you go to 0 degrees Fahrenheit, okay, 0 degrees Celsius, 32 degrees Fahrenheit, you can change the water into a solid we call ice. Okay? Now, if you tried to make ice, or a solid, I should say, of some of those other compounds I mentioned, like H2S or H2SE, you'd have to go far, far further down in temperature. The boiling point of water is 100 degrees Celsius, 212 degrees Fahrenheit. The fascinating thing is that it takes a lot of heat energy to shift it from liquid state to a gaseous state. And that plays a role in why sweating is so important, because it takes away heat energy as it evaporates from your skin. But on top of that, hey, because it takes so much energy to separate the hydrogen bonds, even though they are weak, that gives us the capability of having liquid water on the Earth, even up to the temperature of almost, but not quite, 100 degrees Celsius. Okay? Surface tension, if you've never seen that before. If you've ever seen a water strider, it's an insect that basically sits on top of the water, flits around. Here's an example. Now you see how it's basically standing on the surface tension here. This is, I don't think this is much of a water strider as more a spider. But this is an example that the surface tension is basically the attraction of different water molecules together so they don't get separated. Now, if I did this with something like acetone or gasoline or something else that's a non-polar, that insect would go bloop right through, go sink right down. Here we're adding salt. And what you're getting is this fascinating dissociation that's occurring in the glass of water. Here's a much more clearer model that would give you an understanding. Remember that crystal we had that where basically the chlorides were surrounded by the sodium atoms and the sodium atoms were surrounded by the chloride ions? Well, look, if chlorides are negatively charged and sodiums are positively charged, what happens is that they can be surrounded. For example, the sodium charge can be surrounded by the negative side of the water molecules. Consequently, also, the negative ion, chloride, can be surrounded by the positive sides of the polar molecule water. And that's how water can dissociate ionic compounds. Now, I mentioned about 3 basic types of matter. Solid, which has a constant volume and a fixed shape. Liquids have a constant volume, but no fixed shape. I mean, think about it. It takes the shape of its container. Gas has neither constant volume nor shape. Basically, if you take whether it's 5 gas atoms or 5 million gas atoms, and you put them into a container, they'll just go bouncing around all over the place. There'll be no fixed volume, and they won't take really a shape. They'll basically just bounce off all the sides of the container, take up whatever space is available for the container that holds those gaseous atoms. Now we're going to move from matter for a second into energy and get some understanding here, some of the basics. When we talk about energy, that's the capacity to do work or heat. Now, the reason why is because when you think about it, people used to say, well, what's energy? We can say what it does. The interesting thing is that we can't say what it is. The closest you get is mathematical structures. That's what we call about the poverty of our language. But when we talk about capacity to work, the then question came up, well, what about like when I'm shivering, I'm not doing any work, but I'm creating heat. That's energy. When I talk about work, that's movement in the body or change in physical structure of matter. Okay, fine. There are 2 kinds of energy, basically, kinetic, potential. Kinetic is energy of the material in movement of some type. Potential is stored energy, and this can be stored as a result of some chemical properties, such as what you get in a battery. And when the battery is connected, then you go from potential to kinetic. You have chemical reactions occur, they provide a flow of electrons, we call current. But with kinetic, it's interesting because there can be various amounts of kinetic, and potential does not have to be just chemical stored in bonds. It can be structures that are stored in a position, such as a boulder. If a boulder's on a flat surface, not going to go anywhere. Boulder's on the top of a mountain, it could roll downward. So if it doesn't roll anywhere on the top of that mountain, it's considered stored potential energy. But if you start rolling it, boy, that's using a lot of kinetic energy. Let me move on. Metabolism. These are all the chemical reactions in cells and tissue at any instant. When we talk about catabolic, these are chemical reactions that involve a breakdown, usually from more complex to more simpler molecules, whereas anabolic is going from simpler to build up to more complex molecules. When we talk about energy, though, we have to talk about reactants and products, and we symbolize this with an arrow. So reactants are the substances that take place in a chemical reaction. And then we put an arrow pointing toward products. That is, that reactants will basically create a reaction that will lead you to products. And products are substances produced as a result of a chemical reaction. So think about it this way. You're a cell. Yay. You absorb substances. In the typical cell, it will have chemical reactions, and energy is transferred and used for the essential activities of maintenance and repair, growth, cell division, and special functions. Maybe manufacturing something to be secreted, or maybe producing replacement proteins, etc., etc., etc. There's a method to how we describe chemical reactions. First, though, you have to sit there and say, well, don't we have some standardized quantity? Yes. And the problem is that if I say to you in a classroom, go get me a dozen eggs, and you come in with this big container, and you've got me a dozen eggs, but they're ostrich eggs. They're big. And I say, no, 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 no. Go back and go get me a dozen eggs. Person goes away, comes back with a teeny weeny little box. There are 12 eggs there, but they're sparrow eggs. They're very, very small. I'm like, no, 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 no. Go back and get me some chicken eggs. A dozen. And then she comes back, or he comes back, and they give me the box, and there it is. 1 dozen chicken eggs. Now, if you use this analogy and think about the size of the different eggs I just talked about, that's what you have to deal with when you deal with different atoms. Some atoms are exceedingly small because they're very simple. Just 1 proton, 1 electron, and that's it. You've got hydrogen. Other ones are humongous. Uranium, 92 protons, and then 139, I think it is, something like that. Neutrons, so you got 92 protons, 92 electrons, 139 neutrons. You've got a humongous atom for uranium. So how do you standardize all of these? You take the quantity with its weight in grams. Now, the weight in grams is equal to the element's atomic weight. Remember, the atomic weight is going to be that averaged out number that you see. Sometimes it's with 3, 4, 5 decimals on your periodic table. And so you'd say this is 1 mole. So, for example, 2 moles of hydrogen gas, 1 mole of oxygen gas will give you what? H2O. 1 mole of water molecules. Now, for compounds, the weight in grams is derived from atomic weights of all atoms that make up 1 compound unit. We call it a molecule. The mole is very useful to calculate quantities of reactants required for specific reactions, or to determine quantities of products generated by a specific chemical reaction, which I just gave it to you. 2 moles of hydrogen plus 1 mole of oxygen. Oops, wait a minute. Oxygen is O2, so I've made an error. I'd have to go and say 4 quantities, 4 moles, or no, because hydrogen also is a gas that goes by H2, not H. So it all balances out anyways. But the only thing that you've got to adjust is the number of the products made. So 2 moles of hydrogen gas. 1 mole of oxygen gas gives me 2 moles, H2O, of water. Now, you can see this here. 2 hydrogen atoms, 2 oxygen atoms. Okay, fine. Yeah, that's right. Yeah, okay, fine. Now I've got to make hydrogen molecule, but I got to make some adjustments here because I only have 1 atom of oxygen that goes with the 2 atoms of hydrogen. Okay, fine. That works out. We eventually get this. But see, in reality, you don't get single atoms of oxygen. That's highly reactive in nature. What you do get, oops, sorry about that, is situations, for example, if I was going to talk about atoms or molecule of hydrogen is H2. It's consisting of 2 atoms for every one of these molecules. This is a molecule of hydrogen. Same thing with oxygen, which I've talked about, okay? If you go to the ions, now this is straightforward. You've got sodium and chloride. So 1 mole of sodium and 1 mole of chloride give you 1 mole of sodium chloride. Now you have to be aware of a couple of other things. There are some ions that are created that instead of having a -1 or a +1, they have a +2. In this case, the calcium ion has lost 2 of its electrons. Okay? You need to keep that in mind. And here's some of the notation that you see: 1 mole of oxygen, 1 mole of hydrogen. And I brought this up earlier. Okay? Now, there are basic types of chemical reactions. There's decomposition, which is there's simple, hydrolysis, and catabolism. Okay? There's synthesis, which is simple, dehydration, and anabolism. And then we have exchange reactions. Simple one, decomposition. AB gives you A and B, no problem. Hydrolysis, whenever you see hydrolysis, lysis means break. Hydro refers to water. So when you break the compound, you break also a molecule of water. You will have hydrogen and you will have a hydroxyl group, which is OH. The hydroxyl group will go to one of the final products. The oxygen will go, the hydrogen will go to the other product. Catabolism is something a little bit more complex. When we talk about catabolism, you're talking about something much more complex. Let's say a large protein. You break it down into the individual amino acids that make it up. We're going to be talking a little bit about this, where there are certain building blocks that make up some of the macromolecules: proteins, carbohydrates, lipids, nucleic acids, etc. We'll go into that. When we talk about synthesis, the difference between decomposition and synthesis is very straightforward. Decomposition, breaking down. Synthesis, building up. Simple synthesis, A plus B gives you AB. Dehydration is you lose water. So when you take two basic simpler molecules, one will lose a hydrogen, one will lose a hydroxyl group, the OH, and then you form a water molecule which will leave. Anabolism, well, let's do the opposite of what I was doing a minute ago. I want to make that complex protein. I'm going to bring together a bunch of simpler molecules, individual amino acids, to build up, to make that. And then we have exchange reactions. Well, these are what give you basically these situations here. And by the way, catabolism is one of the key ones. You see here, simple. AB gives you A and B. Hydrolysis, AB plus water gives you one product which has the hydrogen of the water, A. The other one has a hydroxyl group, B. You can see this reaction. CD is broken down to C plus D. And this a lot of times is that with catabolic reactions, you release some energy in the process. So when the bonds are broken and you have the separation of C and D, you end up with a release of energy. The opposite, synthesis. We have simpler compounds, we bring them together, we form something more complex, AB. Here, dehydration, loss of the water molecule. So A gives up its hydrogen, B gives up the hydroxyl group, we form an AB complex, and we also lose a water molecule. You'll see this a lot when we get into making triglycerides, for example. Oops. Finally, AB. Now, here's the interesting thing. If we said catabolism releases energy, anabolism will require energy. And so if you have A plus B, you're going to get AB. And usually you're going to have to insert energy into this. You also have the unique situation of equilibrium. Sometimes what happens is that reactions go back and forth, as you see with these two arrows. One points in this way, A plus B gives you AB. But then it deteriorates and breaks down from AB to A plus B. And these usually proceed in certain balance. We've talked about dehydration synthesis, hydrolysis. You can see an example of this. This is a realistic example. You take glucose plus fructose. In one direction, you have a dehydration synthesis. You lose a water molecule, you make a chemical bond here. This is a covalent bond, and now you have sucrose, table sugar. You want to break down sucrose? Then what you do is you have hydrolysis. You bring water in, and hydrogen goes to one of the building blocks. Hydroxyl goes to the other one. So now you have the dissociation, and you have one molecule of fructose, one molecule of glucose. Okay? Finally, I talked about exchanges. Exchanges occur very rapidly and are very straightforward. If I have AB and I have CD, that means that the A is going to form and connect with the D, hence AD. B is going to combine with the C, and so you're going to have CB. Okay? Now this can occur with atoms, or with electrons, or with hydrogen atoms, so I want you to be aware of that. Factors that affect these reactions. Okay, just like baking, cooking, doing a lot of different things. Temperature is one of the factors that affect the reactions. I mean, think about it. If I was going to take, and I'm just saying this, if I was going to take some of these pre-done brownie mixes, for example, you put it into the pan, you put it into the oven, but I never turned on the oven. So the temperature is not raised to, let's say, 400 degrees for like 10 minutes. Instead, the brownie mix is kind of, gooey. It's still at room temperature, even though I've waited 20 minutes. Nope. I bring it up to 400 degrees for the proper amount of time, and I get brownies. The second factor that will affect reactions is particle size. That's in part why we make some pharmaceuticals extremely fine, bind them together so that the particles will easily be able to dissolve and to act on the patient once they're basically consumed. Other factors that affect the reaction is the concentration of reactants. If I've got a certain amount of A, but I've got only very little of B, I'm only going to have a little bit of this reaction, and I'm going to have this imbalance. I'm going to have this large amount of A that's not going to be reacted. So you have to have the proper quantities of both A and B to get the reaction to occur. That's when we talk about concentration. And finally, we have a catalyst. Catalysts are unique. They're substances that increase the rate of chemical reactions without being chemically altered during the reaction. What does that mean? Basically, catalysts speed up the rate of a chemical reaction, but the catalyst itself doesn't get chemically altered, so it can be reused again and again and again and again. Have you ever heard anyone who's driven down the road and they said, oh, I got to go pay a lot of money now for my catalytic converter? What's a catalytic converter? A catalytic converter is down in the tailpipe, and basically what it does is it has either palladium or platinum particles, and basically the gases run through them, and any unburned gasoline vapors or any other components are broken down as they go through this catalyst, thereby making the pollutants that come out of the tailpipe virtually very, very low and very, very not significant. Okay? Now, we have biological catalysts, and we call them enzymes. We'll get more into that in a bit. When we have basically any chemical reaction that occurs, usually they require some energy to start the chemical reaction. This is called the activation energy. Now, I mentioned to you before that enzymes are biological catalysts. They're protein-based. They basically will increase the rate of chemical reactions without being chemically altered during the reaction. They perform most of the complex synthesis and decomposition reactions that occur in your body, both inside cells and outside cells. They do function in a very selective means. They are very specific for unique reactants. In other words, let me give you an example. Remember that sucrose you saw a few minutes ago? There is an enzyme that's specific to break down sucrose, table sugar. It's called sucrase. It will not break down any other type of molecule, but will work specifically on sucrose to break it down to the simpler components of glucose and fructose. Also, enzymes are very specific about the temperature and the pH conditions. I'll give you an example. If you take pepsin, which is made in your stomach, it is very specific about the pH, very low acidity, very low pH, I should say, that it will work under, and also body temperature. If you brought it down to something like 40 degrees Fahrenheit, it would not work as effectively, if at all. Now, enzymatic reactions are generally reversible. They proceed until the equilibrium is achieved. So here we have reactants and a stable product. Notice the amount of activation energy here. That's a lot. Now, I usually, when I ask my class students, I say, did you have breakfast or did you have lunch, depending on what time it is of the day? And I say to them, okay, now did you have lunch? And they'll say, yes. And I'll say, okay, fine. Now, what did you have? And they'll say, well, let's just take hamburger. They took a hamburger. Okay, fine. Now, they had a hamburger. I said, now, did you break down the hamburger from its proteins to simple amino acids using a important bioreactor where it goes up to 400 or 500 degrees to break down the proteins? And she nods her head, no, what are you kidding me? Did you have your stomach filled with palladium and platinum to break down the proteins? She went, no, of course not. You're at 98.6 body temperature. You have acids in the stomach, which help, but you also have pepsin, which will help break the protein bonds. And the protein bonds between amino acids are covalent bonds. And so you need very little activation energy because the enzyme helps. Notice the amount of activation energy here to go from reactants to stable products. Okay? Now, metabolic pathways are basically a series of interlocking metabolic steps, each dependent on a specific enzyme. So in other words, if I want to go from A to C, I have to first encounter enzyme 1, which will bring me through step 1 to make me into B. B will then be acted on by enzyme 2 in step 2, which will convert me over to C. Okay? Now I can continue this, so forth and so on. The function of the pathway is dependent upon the complete and controlled production of enzymes for each step. One of the things you have to think about is this. We have lots of enzymes that are involved with certain steps, both in disease and in health. Let me give you an example. You hurt yourself. Now, you go over and you take non-steroidal anti-inflammatory drug, let's say aspirin. Let's say ibuprofen. These are drugs that block enzymes that are involved in the process of making prostaglandins, which would create the inflammation and thereby the pain of that injury. That's why they're called pain-relieving drugs, okay? That's why they're called non-steroidal, they're not steroid, anti-inflammatory drugs. So you have certain select drugs that block an enzyme pathway and thereby block the synthesis of a process. Now, all chemical reactions require activation energy. I mentioned that. But once they've started, they either absorb or release energy to achieve the completion. Now, here's the point. Let's go back to my brownie analogy. You know, I need to not only start off with energy. If I only went 400 degrees, let's say, for 1 minute, that's not enough energy. But I have to keep adding energy to have the complete conversion of this reaction. That's one type of these reactions. It's called an endergonic. An endergonic, these reactions require more energy than is released during the reaction. Think about it from another perspective. I'm going to go out and I'm going to get one of those glow sticks. If you've ever seen them, they're basically a reaction. As a chemical reaction releases light. Now, light will be our energy in this case. In an exergonic reaction, they release more energy during the reaction than what is, put in the starting of the reaction. In other words, they get more out of it than the activation energy. Once I break the tube and mix the chemicals together, you immediately get a greater output of energy than just the mere activation energy. You get a tremendous amount. Because instead of the energy we think in, let's say, in heat or in other forms of energy, we're going to get light, but that still qualifies for an exergonic reaction. Now, terms we have to be aware of. Metabolites, these are substances synthesized or broken down by chemical reactions in the body. Nutrients, these are essential metabolites, normally obtained from our diet. We don't make them. We have to consume them. Organic compounds have carbon, except the only one that's not considered an organic compound is carbon dioxide. Now, inorganic compounds do not have carbon. An example of an inorganic compound, real simple, sodium chloride. Okay? Hydrogen peroxide. So far, so good? Good. If you have questions about this, just mosey along. Look even in your kitchen or pantry. You'll find the difference between inorganic compounds and organic compounds. Let's move on because we're going to move now into macromolecules and then go into the 4 essential organic compounds that are necessary for life. Macromolecules, macro means large. So really what we have is a macromolecule is defined as a large molecule made up of monomer subunits. An example, proteins, their subunits, their building blocks in essence are amino acids. When I talk about a monomer, that's one. A monomer is a molecule bonded to many other identical molecules. It will be the building block to make something more complex. A polymer is a molecule made up of many monomers, usually bonded together by covalent bonds. So monomers can make a polymer. The process there is a dehydration synthesis, as you can see in the chart. Polymers can be broken down into monomers. The process there is hydrolysis reactions. Now, let's go back to water for a minute because it really is interesting. When we look at water, the bonding of water molecules contribute to various physical properties. Lubrication. Water is an effective lubricant, reducing friction within joints and in body cavities. We're going to have various joints that we're going to be talking about in Chapter 9. We're going to be talking about this throughout the body. And a lot of times you have these synovial areas that are little encapsulated structures that contain fluid to allow to reduce friction between joints, between bones. And one of the major contributing compounds in that synovial fluid is water. Water plays a critical role in chemical reactions. Many of them, as we're talking about dehydration synthesis or hydrolysis. Water has a high heat capacity. It takes up a lot of energy to basically go from solid, ice, to water. and then takes a much greater amount of energy to bring it up to go from water into a gas we call water vapor. Water is also a solvent for many different substances. You see here, here's a dye capsule that they're basically a dye pill, and you can see that as diffusion occurs, you have the spreading out of this material. Now, physiological systems depend on water. Water is a polar molecule. Water can dissociate ionic compounds. We've talked about the hydration sphere. Now, here's a couple of terms you need to know and understand, because they're going to come up a lot of times throughout this course and the next one. Hydrophilic, hydrophobic. What do I mean by that? Hydrophilic, hydro, obviously water. Philios refers to loving, so it's some compound or something that loves water, hydrophilic. I say hydrophobic, phobos refers to fear, so it's something that does not get along with or repels water. When we talk about electrolytes, these are soluble inorganic substances whose ions will conduct electric current in solution. Electrolytes are critical for proper physiological function. And we've talked about water being the universal solvent. Now, here's where we get into a situation you've probably dealt with a little bit in the lab. What is a solution? A solution is composed of a solvent and a solute. The solvent is always the quantity of material that's in greater quantity. The solute is the substance in lesser quantity. As I give you the example of saline solution, the solvent is the water. The solute is saline or salt. Another way to look at it, though, is that we're not just talking about solutions in the sense of just pure liquids. For example, the air you breathe is a solution. It's composed of the solvent, which would be nitrogen gas. 78% of the atmosphere, 78% of what you breathe in is nitrogen gas. The solute are the other gases in lesser quantities that are mixed in with this gaseous solution. That would be oxygen at 21%, and then we have some water vapor, and we have some pollutants and carbon dioxide, et cetera, et cetera, et cetera. Okay? Here we see basically the dipole for water, which allows for hydrogen bonding. Here we see the dissociation, the hydration spheres that I talked about earlier. If you have a negatively charged ion here, it's going to be surrounded by the positive sides of the water molecules. A positive ion, such as sodium, will be surrounded by the negative parts of a water molecule. Now, other things can dissolve, other things can dissolve in water. Okay? Glucose, it's a sugar. So how does it dissolve? Glucose will basically have water molecules surrounding it. Some of them will be the negative side, and some of them you don't really see a lot of positive sides, but what you do see is water molecules will surround around the glucose molecule. Also electrolytes. Now, if I was to take sodium chloride, put it into water, but then put an electric current, and by putting the electric current, I have the electrodes here. Notice the electrode here is positive. What's going to be drawn to it, as we've talked about before? Charges, opposite charges attract. So these negative ions would be attracted, the chloride ions, to the positive pole. Consequently, the negative pole here will have the sodiums attracted to it. Okay? Now, important electrolytes that dissolve in body fluids. Yes, I do expect you to know these. I expect you not necessarily to know all of the chemistry symbols, but be somewhat familiarized with things like sodium chloride, potassium chloride, calcium phosphate, sodium bicarbonate, magnesium chloride. Right? Those big five you're going to see coming into you time and time again throughout this entire course. So it's going to help you. It would be nice to at least be somewhat familiarized with these other two, the sodium hydrogen phosphate and the sodium sulfate. All of these dissolve in body fluids. Now, when I talk about different types of solutions, you need to be aware of the factors and those things that we see in real life. For a solution, the solute particles are very tiny, and as a result, they're not going to settle out, okay? And they're not going to scatter light. An example of that is mineral water, okay? Some salts are in it, maybe some dissolved carbon dioxide, but it's pretty much transparent. A colloid is solute particles are larger than in a solution and scatter light. They don't settle out. They use the example of gelatin, okay? Here are the solute particles, okay? A suspension is where solute particles are very large. They will settle out, meaning that if you shake up the container and you let them set, you just put it on the table for a few minutes, the particles will start to settle down to the bottom of the container. They may also scatter light, as you can see. Here's an example right here, blood. If you take a sample of blood and spin it down, you're just basically allowing settling, but at a quicker rate. But you'll end up with the heavier particles, which are the red blood cells, white blood cells, and to a lesser part, the thrombocytes. They'll settle out in a certain range, and then above them will be this kind of straw-colored fluid that we call plasma, okay? Now, physiological systems, as I said, have depended on water. So here's an interesting thing. Hydrophobic molecules and proteins. How is it that some proteins can basically interact in water molecules? Well, proteins are made up of amino acids. Some of the amino acids are charged. Therefore, what's going to happen is you're going to have somewhat this hydration shell formulate around it. Wherever there are negative charges on the protein, then the positive sides of the water molecules are going to hang around or be attracted to them. Wherever there are positive sites of the protein, the negative sides of water molecules will attract. Now, what if there were, and there are, amino acids that don't have any charge? They're nonpolar. What happens? That can make the protein not dissolve with the water molecules, and they will basically settle out, okay? Fats and oils are a perfect example of hydrophobic molecules. Think about it this time. Next time you clean, you do dishes or something else like that, you put a greasy dish into the sink in water, and what happens? The fats and oils do not dissolve or mix well with the water. As a matter of fact, the fats and oils will lift up and they will settle on top because they are hydrophobic. Now, we've got to talk about blood fluid pH regulation, which is vital for homeostasis. The pH is a measure of the hydrogen ion concentration. It is defined as a negative logarithm of hydrogen ion concentration in moles per liter. Big long word. What does it mean? Simple. pH is the measure of the hydrogen ion concentrations, and so a lot more of the hydrogen ions, you have a more acidic nature. Very few hydrogen ions, you have more of an alkaline or basic nature. Let's take a look at a real life situation here. Blood pH. Blood pH has a range of 7.35 to 7.45. Now, that's the normal range. If you go below 7.35, that is an abnormal pH, and you're referred to as being in acidosis. If you go above 7.45, that's an abnormal pH, and you're said to go into alkalosis. Okay? The acidity or alkalinity of the blood plays a key role in the function of many chemical reactions, the function of many different proteins, and so that's going to be critical. We're going to go into this in deep depth. AP2, acid base, and renal function. So get some of this down now. It'll help you later on. When I say something is acidic, it has more hydrogen ions than hydroxide ions. Remember that if you take water and you split it, you have a hydrogen ion and you have a hydroxide ion. The hydroxide ion is kind of a negatively charged ion. It has only an oxygen and a hydrogen. The hydrogen ion is a positively charged, and it's just a single hydrogen, virtually just a proton, because hydrogen ion has no electrons. When I say something is basic, or the other term is alkaline, it has more hydroxide ions than hydrogen ions. When I say something is neutral, it is an equal balance of hydrogen ions and hydroxide ions. Neutrality for pH is 7.0. But don't get that confused with blood pH. That range has to be 7.35 to 7.45. And you can see, as we talked about, the hydrogen ion here, the hydroxide ion here. And there is a variety of substances that we talk about. Here's the neutral, pH of 7 is neutral. That's pure water. And you start looking at urine, which can range from about 8 to down as 4.5. Saliva, milk, goes below that, slightly acidic. Tomatoes and grapes, even more acidic. Beer, vinegar, wine, and pickles, much, much more acidic. Then we have stomach hydrochloric acid, which is really at 1. It's extremely acidic. 1 mole per liter of hydrochloric acid is a pH of 0. Okay? And that is the most acidic. Let's go to the other side. If we talk about the pH of eggs, it's slightly closer or slightly above 7.45, because here's the blood pH, 7.35 to 7.45. Seawater varies in its amount, but remember that seawater has a lot of salts and other dissolved minerals in it. Then we get up to household bleach, which is about 9.5. Household ammonia ranges somewhere slightly below 11 and slightly above 12. You're really getting basic now, and then you get to oven cleaner, which is basically some type of sodium hydroxide compound that is extremely basic at about 13.3, and then 1 mole per liter of sodium hydroxide is at a pH of 14. This direction above 7 is basic or alkaline. This direction below 7 is acidic. Now, an acid is a solute that dissolves into solution and releases hydrogen ions. It decreases the pH and can act as a proton donor. Hydrogen ion is really just a proton. Base is a solute that removes hydrogen ions from solution and can act as a proton acceptor. Now, if I have a hydrogen ion join a hydroxide ion, what does that equal? Water, H2O. Weak acids and weak bases do not completely dissociate. An example of that would be acetic acid, which you find in vinegar. Okay, some of the acids will let go of their hydrogen ion, others will not. So you need to be aware of that. Salts. These are ionic compounds that consist of a cation, a positive ion, except for hydrogen, and any anion, a negative ion, except for hydroxide ion. Okay, so here we have hydrochloric acid dissociating into hydrogen and chloride. Here we have sodium hydroxide, a very powerful alkali substance, and it can be dissociated into sodium and the hydroxide, okay, molecule, or hydroxide ion, excuse me. Here we have H2CO3. Now, H2CO3, by the way, is known as carbonic acid. It's an organic acid that you see. It can be dissociated into just hydrogen ion and the bicarbonate ion. This is very important to get down now, because you're going to see this repeatedly in both blood, in kidney, and to a lesser extent in the digestive system. Sodium chloride is an ionic compound that will completely dissociate into sodium and chloride. Buffers. These are compounds that stabilize the pH of a solution by basically removing or adding hydrogen ions. This is extremely important. In other words, think of it this way. Think of buffers as sort of like sponges. They will either remove excess hydrogen ions or they will add excess hydrogen ions to blunt any shifts in pH. These are normally found in body fluids. They help maintain the pH within normal limits. The buffer system consists of a weak acid and its related salt, which acts as a weak base. For example, carbonic acid and the bicarbonate buffer system. Here we have the carbonic acid bicarbonate buffer system, and you'll see this very prominently when we have respiration, and we get into that in AP2. You notice that you have CO2, it mixes with water, and once it gets into the blood, you can form CO2, H2O to carbonic acid. Carbonic acid will many times dissociate immediately into just the hydrogen ion and the bicarbonate ion. Now, this is where we get into what we call the bicarbonate reserve. The negatively charged bicarbonate ion will join with sodium and form sodium bicarbonate. But these can freely dissociate, provide the bicarbonate ion. If there's an excess of hydrogen ions, they will form together, form carbonic acid, and also dissociate back to carbon dioxide and water. What you have to understand is that this system blunts any massive buildup of hydrogen ions, or suddenly this loss of hydrogen ions, and so the system is going alkaline and helps to blunt any major changes. Organic compounds. These contain carbon and hydrogen. Generally, though, a lot of times you're going to find them with some oxygen as well, varying in amount. They're held together by covalent bonds. Some can form long chains, rings, or other structures. Now, when we talk about functional groups, these are groups of atoms that influence the chemical and physical properties of the organic compounds. Four major classes of organic compounds that we're going to be dealing with anatomy and physiology are carbohydrates, proteins, lipids, and nucleic acids. The functional groups are the amino group, as you can see here. This is the rest of the molecule whenever you see the R. Here you see an amino group, which is nitrogen and 2 hydrogens. Here is a carbonyl group. Here's the carbon. It has a double covalent bond to an oxygen and then another bond to basically a hydroxyl group. The hydroxyl group is very simple. It's just oxygen and a hydrogen. And then we have the phosphate group. Now, all of these groups you're going to see as we start talking about the various types of fatty acids, amino acids, carbohydrates, nucleic acids, etc. So I want you to be aware of those now. The phosphate group is a very interesting group. Notice that we've got some negative charges here. But anyways, what you have is a central phosphate, and then you have 4 other atoms surrounding it of oxygen. These may play a key role, particularly in molecules like ATP, the high energy compound molecule that we use to get energy. Okay, ATP stands for adenosine triphosphate. Okay, let's start off with carbohydrates. They contain carbon, hydrogen, and oxygen in a 1 to 2 to 1 ratio. So carbon 1, hydrogen 2, or oxygen 1. Yeah, but sometimes it's going to be a multiple of that. So 2 carbons, 4 hydrogens, 2 oxygens. I think you get the point. This accounts for 1.5% or around there of body weight. It can form straight chains or closed ring structures. It's basically held together by covalent bonds, and covalent bonds can be formed by dehydration synthesis. The covalent bonds can be broken by hydrolysis. Now, this is where you can get complexity, so you need to be aware of this now. You have monosaccharides, disaccharides, and polysaccharides. Monosaccharides, this is a monomer. It's a simple sugar. Example, glucose, fructose, galactose. Disaccharides is when you have 2 monomers held together by a covalent bond. This is where you get sucrose, lactose, maltose. Polysaccharides, poly means many. So you've got many of these saccharides or many of these monomers of sugar molecules, and they can form branch structures or long chains, etc. Cases of that include cellulose, amylose, otherwise known as starch, glycogen, etc. Here we have a simple carbohydrate. Notice that it has a backbone of carbon in a straight chain format, or it can form this ring structure. But whatever you say, notice the hydrogens, notice the hydroxyl groups here, so they bring in oxygen, as well as the presence of the carbon. Notice that some cases, the chemical formula, the number of carbon atoms, hydrogen atoms, and oxygen atoms are the same, but they're in different arrangements. Glucose and fructose have the same formula, but they're arranged in different formats, as you can see here. Okay? And I would encourage you to review this chart just to get further review on the monosaccharides, disaccharides, and polysaccharides. Disaccharides, as I said, they're held together by a covalent bond here. You can see it right over here. Lactose, we're all familiar with lactose. There are people that are lactose intolerant because they lack making the enzyme lactase to break and sever this disaccharide into galactose and glucose. Maltose requires the enzyme maltase, and you have really just two glucoses bonded together. And finally, sucrose would require the enzyme sucrase to break these two apart, and sucrose is basically glucose and fructose together. Notice we have the breakdown or the buildup via basically the buildup here is by dehydration synthesis, and you create the free water molecule, or the reversal of sucrose by hydrolysis breaks down the water molecule, and so the hydrogen goes with the fructose and the hydroxyl group goes with the glucose. Here you have a perfect example, as you see this, of many glucose molecules held together, and this is forming an amylose structure, basically a polysaccharide. And you can see several examples of this. Glycogen is referred to also as animal starch, stored in places such as the skeletal muscle and the liver. You have amylose and amylopectin, and the difference really is in the arrangement of these chains. Are they branched or not branched? Okay. These cases, they're found in plants. Okay. And then, of course, you have cellulose, which we lack an enzyme, cellulase, to break this up to individual glucoses. But people would say, well, what about termites? Termites consume it, but here's the interesting thing. It's not termites themselves that have the cellulase. It is the symbiotic organisms, the protozoal organisms in their gut that basically secrete the cellulase. As you start chopping off glucose molecules, some of them are used by the termites, some of them are used by the termites, microorganisms, to basically feed them and keep them nice and happy. Lipids contain carbon to hydrogen ratio of 1 to 2. Usually in ratio, they're going to be low in oxygen. Familiar types include oils, fats, waxes. Lipids are usually insoluble in water. They require special transporters to travel in the bloodstream. Fatty acids are long chains of carbon and hydrogen, and usually they have a carboxyl group at the end. Now, when we have a saturated fatty acid, along that entire chain, there's no double bonds. When we have an unsaturated fatty acid, it has one double bond in the chain. Polyunsaturated fatty acids have more than one double bond in the chain. Here's what I mean. Here is your chain. Notice that in this entire chain, from carbon to carbon, carbon to carbon, etc., you go all the way down. This is lauric acid, a fatty acid. Here is your carboxyl group here. And you all have, in each one of these lines, it symbolizes single covalent bonds. But in some cases, instead of a straight chain, you could have a kink in that chain. And that's what some fatty acids have. And this is the result of having a double covalent bond. So in other words, the hydrogens are gone, and now you've formed two covalent bonds between these two carbons. As a result, it provides the chain with having somewhat of a kink or directional difference. and it makes them harder to stack up. They tend to have more liquid properties at room temperature, whereas with straight saturated fats, they tend to be solid at room temperature. Now, how do we make a triglyceride? Well, that's simple. We have glycerol, which is attached to the fatty acid chains. Attachment process of fatty acid chains to glycerol, you have a covalent bond formed by dehydration synthesis. If you want to break the covalent bonds, you have a hydrolysis. The number of chains defines the term. If you have monoglyceride, that means that you have glycerol with one fatty acid chain attached to it. If I have a diglyceride that has two fatty acid chains attached to the glycerol, triglycerides are where you have glycerol with three fatty acid chains attached to them. Now, various lipids with modifications are found in the body. Here's a glycerol, and here's where we're going to have basically the dehydration synthesis to fuse fatty acid 3, 2, and 1. That means that you're going to form 1, 2, 3 water molecules. Now, by the way, one other thing to be aware of, not all of these fatty acids have to be identical. As you can see in this formation here, I've got two saturated fatty acids and one that's unsaturated here attached to this glycerol, but they're still all triglyceride. And if I wanted to reverse the reaction, I just have to have a hydrolysis reaction to free up from the glycerol fatty acid 1, 2, and 3. Now, there are representative lipids in our body. Fatty acids, example is lauric acid. Glycerides, those are monoglycerides, triglycerides, diglycerides. There's another type of lipid that's called eicosanoids, and these include prostaglandins and leukotrienes. We're going to talk a little bit about those. Prostaglandins are produced in most body tissues. Then we have steroids, such as cholesterol, and these are structure components of cell membranes, hormones, digestive secretions, and bile, etc. All steroids have the same carbon ring framework, which I'm going to show you in a minute. Then we have something unique. Phospholipids, otherwise known as glycolipids. An example of this is lecithin. And this is where you're going to have the fatty acid attached to a structure that will have somewhat of a polar arrangement. So they're going to create the conditions of what is called amphipathic. In other words, part of the molecule is polar, part of it is nonpolar. And these will be the construction materials that will make up the bulk of the plasma membranes, the cell membranes. But let me go a little bit further into the eicosanoids, etc. Eicosanoids are lipids derived from arachidonic acid. Now, arachidonic acid must be consumed. It's not synthesized by the body. One type of eicosanoid, called leukotrienes, are produced by cells in response to disease or injury. That you see also in situations of asthma, allergic reactions in the respiratory system. Prostaglandins, these are produced by damaged tissues. They stimulate nerve endings to produce the pain sensation. Remember I said before about NSAIDs, non-steroidal anti-inflammatory drugs? They block the synthesis of prostaglandins, and thereby they reduce the pain sensations. Steroids are large lipid molecules with distinct four-ring structure. Functional groups, like we've talked about before, are attached to the four-ring group to create differences in properties. That's why you're going to have a difference, even though they look somewhat the same. You're going to have differences between testosterone, estrogen, aldosterone, progesterone, cholesterol, etc. Here's an example of the arachidonic acid. Okay, so you see it's kind of a bent structure. It's unique. Got double bonds here, etc. And then we have the selective addition of different bonds, of different functional groups, etc., that create the unique eicosanoids that you see. Here's prostaglandin E1, otherwise known as PGE1, thromboxane A2, leukotriene B4. There's a whole variety of them out there. When we go to the steroid, this is what I meant by the 4-ring structure. 1, 2, 3, 4. But notice that it's the functional groups attached on the sides of these rings that determine their different properties and whether they bind to certain receptors in different parts of the body. Now, cholesterol is the basis for all steroids formed in the body, interestingly enough. Okay. Now, here is cholesterol, and then notice the 4-ring structure and then the side rings here. This is a ketone functional group. And you have 2 methyl groups, and then you have a hydroxyl group here. Notice the difference between testosterone and estrogen, for example. Similar. So what you really have to have is an enzyme that's going to basically remove this methyl group, but at the same time, notice that inside of this benzene ring here, you've got 1, 2, 1, 2, 1, 2. So you've got, basically you've got 3 double bonds. And then also you'll notice this, that testosterone, or the difference between estrogen and testosterone here, is this is a hydroxyl group and this is just a ketone unit. Okay? Now, let's get into phospholipids, etc. And these will help us to understand some of the basic building blocks that make up a plasma membrane, a cell membrane. Phospholipids have a phosphate group attached to the diglyceride diglycerides. The phosphate group will have a non-lipid group, and it's also attached, and in the presence, it's present in all the cell membranes. A glycolipid is a carbohydrate that's attached to the diglyceride group, and it's present in all cell membranes as well. Now, both of these are ambipathic molecules, and I explained to you what these are. Ambipathic means that the molecule itself is partly polar, so it's hydrophilic, partly nonpolar, so it's hydrophobic. And this is where you can form micelles. These are clusters of lipid molecules surrounded by water. So basically, the part that's polar or hydrophilic is going to face the outside where the water is. And the hydrophobic fatty acid tails will face inward. Okay, now here's what I'm trying to say. Look, this is 1, 2 fatty acid chains, okay? Notice that we have somewhat our glycerol group, but attached to it is a phosphate group, and this is a non-lipid group. Now, this is what I have for a phospholipid. This is going to be charged here. This is going to be nonpolar here. In a glycolipid, instead of having the phosphate group, I have this extension off of the glycerol, and I have some carbohydrates here. Okay? Now, they simplify this by just basically taking the hydrophilic heads. This would be the carbohydrate part, and this would be the hydrophobic tails for the glycolipid. Same thing here, hydrophobic tails here. This is the phospholipid, and the top part is basically the hydrophilic heads. This is an example of a micelle. Here you have the phospholipids here. Here you're going to have also some of the glycolipids, but they're all capable, they're all hydrophilic. They all love to be interacting with water. These guys here are hydrophobic. They don't like hanging around with water. So they're going to be all on the inside. Now, let's go over to proteins. Proteins have some of the most incredible variety. Get a life. Well, it's true. Proteins are macromolecules composed of amino acids. There's about 20 or a little bit over that different types of amino acids. The amino acids are the building blocks. All amino acids contain nitrogen, oxygen, hydrogen, and carbon. There are 2 amino acids that have sulfur, cysteine and methionine. Now, amino acids have a sort of consistent structure, and then there's a variable part. The consistent structure of a central carbon, an amine group, a carboxyl group, and then the variation comes in what they call the R side group. The R group defines different properties. It can be polar, nonpolar, charged, neutral. It can create hydrophobic properties, or hydrophilic properties. Amino acids are covalently bonded to each other. This is referred to as a peptide bond, but basically it's a covalent bond. Okay, here's our central carbon. Yeah, there's this little hydrogen is up here. Nobody really gives much about that. Here is your amino group. Here is your carboxyl group. And this is what is really makes each amino acid unique, the R group. Now, if you take a look, you can compare several of these amino acids. Here's glycine. Piddly little hydrogen here for its R group. Here's alanine. This is just a methyl group here for its R group, but they give each of these unique properties. Okay? Now I can form a covalent bond. Okay? And basically I would have basically a synthesis here where I have this peptide bond formed. It's a covalent bond. Okay? I'm forming it by the synthesis, the dehydration, and I get a water molecule here. I can reverse this and break it down, and the peptide bond can be broken down through hydrolysis. Now, one point. Yeah, you could do this in a laboratory, but you know what? It works much faster? Certain enzymes that will actually break the bonds in between. Now, yeah, I mentioned this before. Peptide bond can be made by dehydration, synthesis, and by broken down by hydrolysis. Tripeptides and larger are called polypeptides. In other words, those peptides made of 3 or more amino acids are called polypeptides. And polypeptide is another way of saying proteins, but they're kind of smaller. Proteins can vary as large as 10,000 amino acids for a single protein. Okay? Diversity of amino acids. They're 20 different. They lead to a large array of proteins with different properties and sizes. And they have different structural complexity levels. And this is what you really need to get down. Okay? Ready? First is the primary level. That is basically amino acids all covalently bonded together, just like beads on a string. They have very strong bonds. The secondary level is based on interactions of the amine and the carboxylic groups of different amino acids. And this can form basically the polypeptide can lead to formation of what they call alpha helixes. Think of it like a corkscrew or beta pleated sheets. This is like if you ever seen ribbon candy, or basically when you've been folding and you fold sheets over on top of each other. Okay, you got to keep in mind that from secondary onward, secondary, tertiary, you've got a lot of weak bonding here. Tertiary is interactions between the R groups of the various amino acids on the polypeptide, which can form very complex structures. You can get coils, you can get folds, and now you're getting even larger structures that create the three-dimensional shape of the polypeptide. Again, at tertiary level, you basically have weak bonds. Now, quaternary is unique because quaternary you need more than one protein. Each protein is considered a subunit. When you put the subunits together, the interactions of the individual polypeptide chains help form this functional protein complex. Okay? But again, they're held together by weak bonds. To give you an example, hemoglobin. Hemoglobin, as a functional protein, is composed of 2 alpha hemoglobin molecules, 2 beta hemoglobin molecules. When you put them all together, you got a nice functional hemoglobin molecule. You take them apart, they don't function as well. Okay? And their functions are directly related to the proper structure and arrangement at the quaternary level. Here's our primary structure, just like beads on a string, okay? In between A1 and A2, and then A2 and A3, that's the peptide bond. Then we go to the secondary structure. So we can have an alpha helix. And that's basically due to hydrogen bonding between one set of amino acids and another that can create this unique spiral shape or the beta sheet, which is kind of like twist back, flattened out, and it's like folded upon each other. Now, once you get to tertiary structure, now you've got your alpha helixes and your beta sheets, as well as other complexes. And in this case, you notice that there's a heme unit here. Well, that's yes, hemoglobin. But this is going to form sort of like a huge glove, a pocket where the heme unit is going to be stored. Okay? Now, you've got to be aware of not only now here I've had my two alphas and my two betas, and I've got a massive functional hemoglobin. This is because of the quaternary structure. But quaternary structure is not just kind of rounded globular proteins. No, it can work for also fibrous proteins. This is two of the major types of quaternary structure you're going to see. It looks like a kind of a lumpy looking globular structure that might be for a globular protein. You might see this in things like, of course, hemoglobin, actin, myosin, all sorts of muscular proteins, etc. But then you've got others that are more like cables, where each strand is a particular protein and they all basically are folded or bent together to form a much stronger fibrous protein. Okay? So each individual strand of that protein contributes to the strength or resiliency or other properties of that particular fibrous shape of the protein. Now, we've been talking about making proteins and having shape, etc. Can you lose the shape? Yes, indeed. This is where we get into the concept of denaturation. This is the process of removing a three-dimensional structural design of a protein with the subsequent loss of protein function. Whoa, doesn't that sound like chapter 1? Structure relates to function. Function relates to structure. Lose the structure, you lose the function. Everybody clear on that? Yeah, you can have denaturation. And I mentioned that. Now, how can you lose the structure? Remember that a lot of what holds together at the secondary level, tertiary level, and quaternary level are basically hydrogen bonds and other weak forms of intermolecular bonds. They're all weak. They can all be broken down by just a moderate application of heat. There are a variety of other ways to do that, but we'll just use heat for an example. Now, as I said, there are a variety of other factors. Besides heat, you can also denature proteins by pH changes, by the presence of acids or bases, by heavy metals. Well, what do you mean by that? Well, if you think about it, why did we use lead in paint? And everybody went bugaboos after a while, and then we banned it. You see, lead was added to paint. You know what the basics of really paint was? Well, if you took milk and you mixed it with water, that was the original first paint. And in some cases, what they did was they used iron rust, and that's where you got, like the red barns that you see and everything else, because it was cheap and, it was well before the time of like Sherwin-Williams and all the other paint makers. Basics of paint were just to coat a surface. We added chemicals, we added color later. But one of the things we also added was something that you wanted to stop happening. And that was the formation of molds and mildew on the surfaces. So you added compounds like lead to stop the formation of molds and mildew. Problem was, the paint would chip off and it could become easy for children to consume, or it would poison the soil. So they dumped paint. Now, why does lead do what it does to children? And it inhibits the brain development. Because the heavy metal of lead will interfere with the structures of certain proteins and certain enzymes, which are proteins also, in a growing brain. And therefore, it will not grow properly. Here's another one. Denaturing chemicals. What are they? Urea, formaldehyde. Why do we preserve animals that we're going to dissect in formaldehyde? Why do we pump formaldehyde or formalin? into a body after it's dead. Because what we want to do is stop the enzymes that begin putrefaction, the decay and breakdown of the body. Okay? And so what happens is you pump this chemical throughout the system and you stop the body from breaking down. So you can have things like funerals and open casket and all this other stuff. And by the way, let me give you my famous teacup exercise. Used to be years ago. I would go in to restaurants and I'd ask for a cup of tea. The waitress, of course, would be very nice and say, "Would you like cream or lemon?" And I would say both. And she would look at me and she'd go, "Oh, sir, you can't do that." I said, "Yes, I can. Just do it." Now, let me tell you what's going on. They would bring you this little teapot almost. It's just filled with hot water. You put the tea bag into the cup. You pour the hot water in. And what happens is you have a high temperature of the water. You have the tannins, which are somewhat acidic. They're going to start dropping the pH of the water. Then I add the cream. Now the cream is really milk that has certain milk proteins in it, like casein. Now casein is water soluble on its own. But then I add the lemon. Now what has happened? I've strained and stressed the casein protein with the heat from the hot water and with the tannins. And now I've further done this with the lemon, which drops the pH to about 4, 3, pH of 4, pH of 3. And what happens is suddenly I get all this flock, this floating white goop. And that is the caseins that have come out. They've lost their secondary and tertiary structure and become insoluble. And it looks like a floating flocculent material. I'll drink it anyways, doesn't matter. But what has happened is I have denatured the proteins that are in the cream by the combination of heat and pH. Therefore, it loses its property to be water soluble and becomes water insoluble. Let's also take egg white before and after heating, for example. Raw egg, you've got the white, and it's got a lot of very interesting proteins, etc. But they have a very transparent property here. Heat up the egg, and all of these proteins in here lose their shape and structure, become denatured, and as a result become very opaque. I hope that helps. Now, I got to take a minute and go further into enzymes. They have important regulatory functions. They're organic catalysts. Reactants in enzymatic reactions are called substrates. This is unique, but you need to get it down. Now, substances produced by an enzymatic reaction are called products. So you would have substrate, arrow pointing toward product. Site where the chemical reaction occurs on enzymes is called the active site. So there's a unique little pocket or something where the substrates will bind to the active site on the enzymes, and they'll form what is briefly called an enzyme substrate complex. As the chemical reaction occurs, temporarily reversible shape change occurs in the enzyme. And what will happen eventually is the final product will pop out from this active site once the chemical reaction has occurred. Now, there's a term you need to be aware of, saturation limit. This is the substrate concentration for the maximum reaction rate. In other words, you can just add so much of the substrate. And the enzymes, because they're constantly doing these reactions and then kicking out the products and doing more reactions, etc., but you can overload them. And eventually you have more substrate than the enzyme molecules that are present can handle at any one time. Remember, enzymes are going to work in some cases at the rate of hundreds, thousands, if not nearly millions of reactions per second. Enzymes usually catalyze synthesis, decomposition, or provide for exchange reactions. Now keep in mind that enzymes are proteins. Hence, they can be denatured to be inactivated. Like I told you earlier, what we do is we pump formalin or formaldehyde into bodies, and therefore the putrefying or decaying enzymes that would break down tissue are stopped in their tracks by these chemicals. Okay? So here we see this diagram where you have the substrates coming in, 1 and 2. They meet into the active site. The substrate complex is now formed for this very, very brief instant where you have a chemical reaction that is occurring. And as soon as the product is formed, it's popped out of the active site. Okay? Now, I've talked about this. Enzymes usually catalyze synthesis, decomposition, or exchange reactions. When the reaction requires an energy donor, the donor is usually a high energy compound. This is where we're going to get into ATP. The high energy compound, well, the best ones contain high energy bonds. And this is usually in the form of covalent bonds, which upon breakage release large amounts of energy. One of the best molecules that's known, most common in the body, is adenosine triphosphate. Tri meaning 3. The formation of ATP from ADP, adenosine diphosphate, is a reversible reaction. Hydrolytic breakdown of ATP requires the enzyme adenosine triphosphatase, ATPase. Okay? And so, adenosine triphosphate, notice this is the adenosine up here. You want adenosine monophosphate, just one phosphate group it's attached here. That's AMP. You want adenosine diphosphate, ADP, you have 2 phosphate groups. Now, each one of these here and here are high energy bonds. So when you have ATP, you've got the maximum amount of energy here, and you have 3 phosphates here. You can take adenosine diphosphate with another phosphate molecule and fuse that phosphate to this and make adenosine triphosphate. For example, ADP, and you see the 2 phosphates down here, plus energy with the phosphate gives you ATP, 3 phosphates, as well as a molecule of water. This gets us into nucleic acids. Now, the 2 best known are DNA and RNA. Nucleic acids are macromolecules composed of carbon, hydrogen, oxygen, nitrogen, and phosphorus. Monomers are called nucleotides. DNA refers to, it's basically short for deoxyribonucleic acid. RNA is short for ribonucleic acid. Now, in the nucleotides, they all consist of 3 main components. A nitrogenous base, meaning contains nitrogen in that particular base structure, a phosphate group, and a sugar. Now, there are different types of nucleotides. The purines are basically adenine and guanine, and we symbolize them a lot of times by just a single letter, A or G. The pyrimidines are cytosine and thymine. Now, thymine's tricky because thymine will only exist in DNA. Uracil only exists in RNA. As you can see here, this is a nucleotide. The nitrogenous base, the sugar, and the phosphate group. The purines are adenine and guanine. The pyrimidines are cytosine. Thymine is found only in DNA. Uracil is found in RNA. The backbone of any nucleic acid is composed of sugar and phosphate groups. Adjacent nucleotides are added by a dehydration synthesis. In both DNA and RNA, the sequence of nitrogen bases carries information for the protein synthesis. When you compare DNA and RNA for differences in composition and structure, you are expected to know them. Here is a comparison chart. I encourage you to know them, cold, hard, and fast. Okay? Here's an example up here of 2 nucleotides undergoing a dehydration synthesis, which will now form the backbone here. Okay? So you've got basically the nucleotides right here, this is basically the nitrogen-containing bases. This is the phosphates, and these are the sugars. So you have sugar, phosphate, as the backbone. Complementary strands of DNA are held together by hydrogen bonds. Remember we talked about those earlier? They're very weak bonds, but they play an important role. Complementary strands due to the complementary base pairing of nitrogen bases. You'll always have this complementary bonding of A's with T's. In DNA, adenines will always bind over in hydrogen bonding with thymines. Cytosines will always bind with guanines. RNA base pairing will occur periodically, and it will create a three-dimensional folded shape for RNA. With that, you're going to have RNA pairing with A's, adenine, with uracil. C's bonding, pairing up with guanine. As you can see here, here's DNA. A's with T's, G's with C's, C's with G's, T's with A's, etc. Okay? The hydrogen bonding between cytosine and guanine is different from adenine and thymine. That's why you don't get any cross bonding, because adenine and thymine only have 2 hydrogen bonds exchanged. Cytosine and guanine have 3. Now, if you have that single strand sugar phosphate backbone, this is where your nitrogenous bases are. Okay? Well, that pretty much covers this chapter. The next area we're going to deal with is chapter 3. That's going to be the cellular level for organization. In the meantime, I do encourage you to review the chapter outline, which is on pages 89 to 91. Review questions are on pages 91 to 92. There are section reviews on pages 60, 68, 74, and 88. Also, don't forget to do the quiz and the homework in mastering A and P. See you next lecture.